sensors can read up to 2 decimal points. But when we are writing this code, we don't want decimals because it just makes things confusing. So we have DO, which is the next 4, and we have temperature, which is the next 4. When you see these long string of numbers, it's really not that easy to understand what you're seeing. So what we did was, the next thing is we have a LabVIEW program to take the string and convert it into a database. So here's our LabVIEW program, basically saying, here's all 14 characters, and here's what's going to happen with them. So the first 2 come over here to give us our node, or which sensor we're reading from. The next 4, with a series of math functions, take it back to pH with the decimal point in place. And then the next 4, DO, the next 4, temperature. And it gives us this really nice readout. Again, node, pH, oxygen, and temperature. And then we'll continue to run here and upload into a database. As far as communicating wirelessly, we use the Zigbee protocol, which allows us to set up one Arduino as a coordinator, and all of the other Arduinos with the XB are going to send the signal to that coordinator. They have a range of 20 meters, but also a benefit of our system is that it doesn't have to directly connect to the coordinator because we have routers. Go ahead and go to the next one. We have what are called routers or end devices, and they can send the signal from one Arduino that's taking signal to another Arduino that's taking signal to another one, and then eventually get back to our coordinator. They don't have to all be within 20 meters of the coordinator, which allows us to really take this as far as we want. We looked it up, and with one coordinator, it said something like 64,000 nodes can be attached to that one coordinator. So this network could go as large as we really want it to.
Some of the peer reviews that we looked up, environmental sensor networks and ecological research. And the first one just talked about how the revolutionary advances have been made. I'm not going to read it to you, but I think it was interesting how that they have continuously worked to design the network sensors and tested them and are able to use them in different areas, such as one of the articles that I was reading talks about dams and how they use them to regulate the water level. And then it also talked about wastewater plants and irrigational systems, how they were able to open and close the gates. And I think we're going to have, that's going to be a part of our overall project, the way I'm understanding it. That's the part that we'll also be able to participate in. Again, this one explained that there had been slow progress in using the wireless sensor networks, and we also discussed that, and Ishin was able to explain that to us, and then Dr. Acevedo talked about the wireless while we were out on our field trips. So it kind of backs up what they were saying. And at this point in our project, I think they're installing FiOS so that we can have wireless, and we were using the XB, which is the wireless. So I'm curious to see if it's actually going to work when we get out there, if they're able to actually install it. Again, this is the application and evaluation of high-power Zigbee-based wireless sensor, exactly what we're using. And again, it has been used in irrigational systems and to control the water flow. And they were saying that it's low cost, easy to install, and it describes how multiple sensors are used to detect the level in the rest of our area. And this particular study was done in Malaysia. That's what I read about. Now, the lesson plan. The subject areas that we're addressing are going to be biology and chemistry on middle school and their high school. So our focus is using the sensors to monitor dissolved oxygen, pH and temperature in our streams. Just what we're doing, and we're basically gonna do mock setups. In 7th grade, we are basically life science, and we do study photosynthesis, respiration. Now, we have not used, we've had basic temperature probes and the digital probes, but we haven't used the Pasco probes and the Vernier probes like some of the other schools have. We do have that equipment at our schools. It just had not been given out. I found out we have a closet full of electronics that has not been used. So we're going to be using that, and basically the students are going to set up. They're going to, well, let's talk about the engineering connection. The sensors are going to be used to monitor, that are used to monitor streams, are designed by engineers. And what I am going to do is do a PowerPoint to introduce it to my class as showing exactly what we did here. And then I'm also going to show them some slides of areas where temperature has impacted the lakes and streams where you have dead fish. I've got some examples of those. And so that they understand how important engineering is to our environmentalists, okay, in resolving issues related to the health of our lakes and streams. Okay, Zach named this Bubble Bubble D.O. Trouble. And what we're going to be doing is eco bottles. They're going to actually set up using 2-liter bottles, and we're going to set up experimental streams. The students will have, there'll be 5 bottles, and what they'll do is they will, in one bottle, we'll have our control bottle, which will be just water. And then they'll have another bottle with plants, another bottle with plants, water, and fish. And they'll explore the relationship between dissolved oxygen and temperature. We're going to focus just like we did here. And then they're going to collect data and with using, again, Pasco or Vernier probes, and so that they can determine the relationship between dissolved oxygen and temperature, and then they'll have some analysis questions to do a comparison also between what the limitations of what our probes can do, but then why we need engineers and technology to be able to go out into the field.
Now, bear in mind, we are going to tell the kids they need to bring their own 2-liter bottles and things like that. Don't be surprised when someone brings the bottom bottle.
No, I did not even see, this bottle has plants, fish, and water, but I did not see that it was a vodka, so that's my problem.
Oh.
You noticed it.
I go, why'd you put a vodka bottle in it? She's like, what are you talking about?
Oh.
Apparently I drank too much.
I will replace that picture.
All right, so what's next? Well, going forward, we've still got 3 more weeks of work to do. One of the things we have to get set up and running is our control system. We talked a little bit about that. The idea is we're going to monitor water level. Wow, words are hard. And use that as our control for these systems, okay? In any system where you've got an aquatic environment, water level becomes important. If it's too high, you overflow the system. That's a problem. A, wasting money and water. B, you don't know what's going to bleed out of that tank. It can throw things off. So you need a way to shut it off, bleed water out if it gets too high. Likewise, if water gets too low, you can start stranding fish. They can get too hot. They can run out of oxygen. All kinds of bad things can happen. So if it goes too low, you need a way to improve that. We've looked at a couple different ways to track water level. They make conductive strips that you can stick on the wall, and pressure strips, and all kinds of stuff. Those have a fairly limited range, as long as you're not looking at a max-min difference of 8 inches, or of less than 8 inches, you're fine. But if you need more flux than that, you need a different solution. So we were looking for something that would work in all cases. To that end, we've decided to go ultrasonic. Measure the difference in height, set a norm. If it goes outside one range, it's too high, you open a valve, bleed some water off until it gets within the acceptable value, close the valve. If it gets too low, there's another valve you open up, dump water in, until the water goes back into acceptable levels, cut it off, everything's good. So that's a very basic, just monitor water level, but there's a little more to it than that. You can also set alarms to watch for pH going too high or too low if ammonia and nitrates go crazy. Dissolved oxygen, and temperature spiking because it's the summer in Texas. Temperature goes way up, DO goes way down in conjunction with that, you got a problem. If that happens, you can flush the tank, which means you're opening both valves. You're bleeding water off and feeding water in at the same time until you get enough fresh water in there that all of the readings are coming back at an acceptable level. Close both valves, system control. Make sense? Sweet. Next slide. This is maybe my favorite slide. Last year at the end, we started talking about doing kind of a big brother system where we put cameras out at the field station to actually monitor what's going on. And that's one of the other things we're going to work on. We're waiting on some video cameras at this point. The ones we had originally are not going to work. There are about 1.5 million problems, being conservative, with making this work. First and foremost, everything I've read anywhere on the internet absolutely says, yeah, good luck streaming video over an Arduino, it's not going to happen. They simply don't have the processing power. You can send digital stills, but you're looking at 1 every 5 minutes. That's not real helpful for what we're looking at. Over the last year, I've been looking at using the Raspberry Pi or the BeagleBone, which are both Linux-based and a little bit heftier processors that are still similar to the Arduino. I don't think they're going to cut it. They're closer, but I'm not sure they can push big enough data packets to make that work either. I'm pretty sure at this point, unless we stumble across something that I'm just unaware of, we're going to have to go with a laptop or a small dedicated computer, something like that, and actually set up a field research station to put a video camera, much less the 4 that we're intending to set up. So it's a beautiful idea, I really like it, but I'm not sure it's going to fly.
We bought a building, it hasn't
mentioned
been built yet.
Yeah, and it'll be air conditioned and they're going to run FiOS out to it, and that's what makes this possible at all. Yeah, that's great news, and I do appreciate you mentioning that because that's something I should have said. But I mean, that's why we can even try it. Putting it in an enclosed system and just dropping it in the field, which was the original dream, is not possible given the limits of the technology we have right now. I'm sure it could be done, but now we're getting back into engineering degrees that we don't have. So we'll explore, see what we can look for, and that'll be something we include in our research paper for further research kind of ideas. But we should be able to get some kind of visual. It is important. And the reason it's important is you are occasionally going to get really weird readings from streams that can be very easily explained if you just see what's going on.